the moon has ever been the object of curiosity for humanity. It's a common sight in our night sky, a moon huge and near enough that its lovely and spooky details can be seen with the naked eye. Humanity walked on the moon more than 5 decades ago, but up to this day, there's still so much we don't know about it, because to go and explore any planet beyond Earth is always vastly dangerous and challenging. Although the moon appears to be a rather alien kind of world compared to Earth, there's one aspect that gets scientists hyped about potential colonization opportunities in the future. There is mounting proof of water on the moon. But lunar water is enigmatic. It does not necessarily appear where we think it will, and by all descriptions it shouldn't appear where we do. Its secrets are ones that the world's nations are eager to unlock, because lunar water is the solution that could open up the solar system to us. Whoever solves it first will gain lots of advantages. Where is lunar water? How do we know that it exists? And how close are we to overcoming the biggest threats of the moon in order to obtain it? Scientists were not always aware that water was on the moon. Luna 24 was a bold robotic mission of the Soviet Union in 1976. It landed on the moon, drilled into the lunar surface approximately 2 meters deep, and returned approximately 170 grams of lunar soil samples to Earth. Of most astonishment to the scientists was the presence of water in the returned sample. Approximately 0.1% of the sample was water, and they found that the concentration of water increased with depth. However, like the very trace amounts of water detected in samples obtained during earlier moon missions, for example Apollo 11, this was assumed to be contamination from Earth. The question whether there is water on the moon remained unanswered. In 1994, NASA's Clementine mission showed the permanently shadowed regions that have not seen any sunlight in billions of years do exist just off to the side of the moon's south pole. Due to this, there was much buzz in the science community on whether frozen ice might exist at the bottom of such craters, shielded from the intense beams of sunlight, where temperatures would never climb above roughly 173 degrees, 280 degrees Celsius. Any water ice in the bottom of such craters could most likely last indefinitely at such temperatures. Elated by this find, NASA sent the Lunar Prospector spacecraft soon after in 1998, specifically to search for evidence that water may be present there. Though it didn't provide us with any definitive solutions to the enigma, it certainly fueled the mystery. The Lunar Prospector found significant amounts of hydrogen at the moon's poles with the use of spectroscopy from orbit. Evidence from Prospector indicated there may be between 10 and 300 million tons of water ice distributed within craters near the lunar poles. But it takes a lot of hydrogen to be present in order for it necessarily to indicate the existence of water, but rather it may be water's closest chemical cousin, hydroxyl, OH. The Prospector spacecraft then crashed on the moon's south pole in 1999. NASA scientists, with the expectation that the impact would send ejecta flying into space, illuminated by the sun, so that they could utilize spectroscopy to demonstrate the presence of water in the dark craters on the moon with Earth-based telescopes. No water ice was unfortunately found from the Lunar Prospector's legacy. The enigma remained. Japan's Selene or Kaguya spacecraft was launched in 2007, and it was on a mission to capture high-resolution photos of the moon and chart the lunar surface. But it too was not able to pick up any evidence for water ice in permanently shaded craters near the south pole of the moon. So after orbiting for 18 months, it too deliberately crashed into the moon, with the hope that this time it would eject sufficient ejecta into space for Earth-based observatories to function with. But once more, no water evidence was detected. India launched its first moon mission, Chandrayaan-1, in 2008. Chandrayaan-1 differed from earlier missions in the sense that instead of depending on sensors to find water from afar, India had on board an impactor that could actually sense water in its gaseous phase using spectroscopy as it moved in close proximity to the spacecraft. Scientists felt water vapor may be present in the very tenuous atmosphere of the Moon just above these craters. The impactor probe was dropped from the main spacecraft body and descended for 25 minutes before it exploded close to a crater at the south pole of the Moon. While it was descending, it transmitted the data to the Chandrayaan-1 mothership, and, among that data, was the solution scientists had searched for all these years: a proof of water. And a few months later, the Moon Mineralogy Mapper satellite on board Chandrayaan-1, with orbit spectroscopy, also found evidence of water on the Moon. But NASA needed more confirmation. They sent their own Lunar Crater Observation and Sensing satellite mission and the LRO, an orbiter you'll be very well acquainted with if you watch this channel. LCROSS was a straightforward, low-cost, fast-track mission, and it had only one main goal: that of once and for all verifying the existence or non-existence of water ice in a permanently shadowed crater close to a lunar polar area. It was a straightforward, simple, but very ingenious design. In a quite rare gesture, the initial phase of the Atlas V rocket LCROSS remained attached to the spacecraft when it reached the Moon. It was released to crash into one of the dark craters at the south pole of the Moon. This was just like how Lunar Prospector and Japan's Kaguya probes crashed into the Moon to send out a debris plume that rose into the lunar surface. But whereas the LCROSS spacecraft itself journeyed through the debris and gathered information without having to base it on Earth-based observatories, which obviously weren't highly reliable for observing small plumes of debris. As debris cloud ascended above the rim of the crater and was illuminated by sunlight, any water ice and other molecules of concern were vaporized and dismantled into their elementary building block, which the sensors on board LCROSS could identify, only to crash into the Moon as well, after doing its job. This union of impacts yielded a vast plume of surface material which the LRO had to investigate. The information received from this mission indicated that lunar soil in dark craters is full of useful compounds, including hydrogen gas, ammonia, and methane, which could be utilized in the manufacture of fuel for space missions. And it even resolved the argument of whether or not there was water, as the evidence strongly indicated that hydrogen found near the poles of the Moon does in fact belong to crystals of water ice. Today, an astonishing 600 billion ki of water ice is estimated to exist on our Moon, about the same weight as 461,538 and 462 cars. That's a lot of water. But how could water of such type be present on the Moon, especially in ice form? Wouldn't it have been evaporated out into space, especially under the intense daytime heat? NASA's Lunar Reconnaissance mission measured surface temperatures of up to 127 degrees Celsius on regions of the Moon in direct sunlight. But again, it is all in that phrase: direct sunlight. In the dark side of the Moon, temperatures drop as low as minus 240 degrees Celsius, which is plenty cold enough to freeze water. These wildly varying temperatures may still be a nuisance to water ice if it weren't for an interesting characteristic of the Moon's rotation. The Moon is inclined at a low angle to the Earth's ecliptic plane about the Sun, with an inclination angle of 5 degrees. It is thought that comets with water billions of years ago crashed into the surface of the Moon, making it possible for craters and depressions in polar areas to collect water. Due to the Moon's low inclination, some of these craters never experienced sunlight for millions of years, enabling this accumulated water to freeze and undisturbed by sunlight, thereby providing an explanation to Chandrayaan-1's observations. LRO also shed more light into the water of the Moon. It was previously believed that the Moon's surface was dead and dry. If water was present, it would be located only in tiny reservoirs in permanently shadowed areas, PSRs. But as LRO passed over the lunar terrain, it started to detect something unusual. Tiny amounts of water molecules would be present on the upper surface of regolith, the gray rock that comprises a lot of the Moon. Turns out the entire Moon is ever so slightly damp. This dampness was even seen to travel through in a kind of lunar water cycle, both by location and by time of day. At noon, when the surface of the moon was hottest, the water appeared to dissipate, but would come back again with the evening. Today, it is estimated that 600 billion kilograms of water, ice, are present on our moon, about the same weight as 461 million cars. That is a lot of water. But how could such water possibly exist on the moon, especially in the form of ice? Wouldn't it have evaporated out of space, especially under the scorching daytime temperatures? NASA's Lunar Reconnaissance mission measured surface temperatures up to 127 degrees Celsius, parts of the moon, in sunlight. So, something is either producing the water, or something must be holding it there. There are a number of theories as to why this could be occurring. Micrometeorites pouring down on the surface of the moon, with small quantities of water, might drop the water onto the lunar surface when it hits. Another option is that a two-stage process in which the sun's solar wind brings hydrogen to the surface and creates a chemical interaction with oxygen-containing minerals in the ground that produces hydroxyl. Simultaneously, micrometeorite bombardment can be transforming that hydroxyl into water. It could then be trapped into tiny bead-like structures in the soil that form out of the high heat created by micrometeorite impacts, or the water could be hidden between grains of lunar soil and sheltered from the sunlight. But LRO's observation that doubles the potential sites on the moon that could be suitable for a lunar base is suddenly that much broader. If this trace quantity of water could be gathered, you would not have to construct your base alongside a permanently shadowed area, which is good because PSRs are significantly colder than we initially supposed. The moon does not have much axial tilt, a bit over a single degree. This means that on the poles there are craters that are never directly facing the sun. Regardless of the time of day or year, the sun never shines directly or never directly facing the sun. Regardless of the time of day or year, the sun never shines light into their dark basins. Of course, a place that doesn't receive any sun is likely to be chilly, but scientists weren't ready for just how chilly it actually was in these areas. To put it in perspective, at the equator on the moon, temperatures range from 120 deg in the daytime to 130 deg in nighttime. LRO carries a diviner instrument, which employs 7 thermal infrared channels to monitor surface temperatures. It was with this that LRO discovered a polar crater whose temperatures reached 250 degrees, the lowest temperature recorded on any object in the whole solar system. That's colder than the mean temperatures of Uranus, Neptune, or even Pluto. The crater edges shielding these areas from solar radiation might have created the perfect storage location for housing water ice. But other, more interesting, useful compounds could be found down there too. Carbon dioxide, carbon monoxide, dinitrogen, and argon, perhaps. It didn't stop there. NASA's SOFIA, Stratospheric Observatory for Infrared Astronomy, discovered water on the sunlit surface of the moon. Its findings verified that water on the moon could be not only confined to cold and shaded regions, but could be spread out all over the lunar surface. SOFIA discovered that the Clavius crater, which is one of the largest craters on Earth that can be seen with the naked eye, has water in concentrations of 100 to 412 parts per million. To put that into perspective, the Sahara Desert has 100 times the amount of water than what SOFIA detected in the lunar soil. So yes, that is an astonishingly low quantity, and it might not be of much use to us, but it helps us in learning about the moon's surface and how it operates. Water is referred to as the oil of space, and developing a successful and cost-effective means of mining it on the moon would be revolutionary in the space industry. It can be recycled within a lunar habitat and utilized for drinking water or cleaning. It could also be used to help plants grow on the moon, which are needed to nourish future lunar colonists. But the biggest and most immediate application for lunar water is making rocket propellant. Hydrogen and oxygen are 2 of the biggest materials that are used to power rockets right now. You see, getting stuff into space from Earth is a very fuel-intensive and expensive process, and the deeper into space you want to go, the more fuel you need, and the more fuel you have to carry. Having to bring all this from Earth heavily limits space exploration. But the Moon has 1/6 of Earth's gravity. So if we are able to successfully produce rocket propellant on the Moon, it's less resource-intensive, and transporting propellant from the Moon to other locations in space would be nowhere near as expensive as transporting it from Earth. And actually, getting something from the Moon to low Earth orbit is less resource-intensive than sending it from Earth itself, even though that adds 300,000 kilometers to the journey. So the presence of water on the Moon could help make space missions more affordable and dramatically increase our capabilities of exploring the solar system. China, along with Russia and other nations, is set to launch 3 missions by 2029, named Chang'e 6, 7, and 8, which will be aimed at the South Pole, where they intend to set up by 2030 a robotic base. The U.S. also intends to have a lunar base by 2030 on the lunar South Pole with NASA's Artemis program. They intend to launch their initial non-manned flight test Artemis 1, followed by a crewed flight test Artemis 2, and then launch Artemis 3, which will occur no sooner than 2025. And that could be our first manned mission to the Moon since 1972. All in all, on the Moon, the real estate market is skyrocketing. While I'm being a little tongue-in-cheek when I say that, it is evident that interest in the Moon as a permanent base for human life is increasing. Before December 2022, the number of countries and political unions that had successfully deployed probes either to orbit or land on the Moon had increased to 6. America, Russia, Japan, Europe, China, and India have all launched spacecraft to our nearest lunar neighbor. Since more and more countries and corporations are looking towards space, it got me thinking, what do we actually want? Do we just want to be a space-faring species, venturing into the solar system for the good of man? Or do humans see profits in space? During my research for this video, I learned plenty of mind-opening things as to why mining in space, and particularly on our Moon, could very well be something that we see taking place in the next few decades. Why? Well, just wait until you hear what's really there to be mined. The first material is called helium-3. You might have read about helium-3 in science fiction, as they propose it as the perfect material for a clean form of nuclear reactor, no radiation and no hazardous byproduct. It also has medical applications and in radiation detectors, but it is actually very scarce on Earth. It does naturally and can be found in deposits of natural gas, for instance, but it's generally not viable to extract, as even in natural gas there are only around 100 parts per billion. So let's say we had 1 billion M3 of natural gas, you'd only be able to extract around 15 kilos of helium-3 from it. Most of the time that is not economically possible. We can also make helium-3 as a waste product of the radioactive decay of tritium. The issue with that, however, is that tritium is an important ingredient of nuclear weapons, and so when the world decreased the production of nuclear weapons, helium-3 stockpiles also started to diminish. Assuming we don't want more tritium in the world, it means we need to find another source of helium-3, especially if technology improves enough for helium-3 reactors to become a reality. Fortunately, we have a world in orbit around Earth right now which has been bombarded by helium-3 for billions of years, thanks to the Sun. Earth's magnetic field takes helium-3 traveling with the solar wind around our planet, while the Moon, having no magnetic field for cover, just absorbs it in the upper layer of the ground. We're not discussing huge amounts. It has a maximum of 50 parts per billion. But since it's everywhere on the Moon, and not only in small reservoirs, it can be gathered in conjunction with any other lunar mining venture. It could also be employed to fuel reactors on the Moon itself, making a Moon base energy independent. Some believe that helium-3 mining on the Moon will not be feasible, though China maintains that sooner or later mining helium-3 is one of the main aims of their Chinese lunar exploration program. American, European, and Indian researchers have all said it is something that they will look into further, and Russia is carrying out a feasibility study on this today. Even corporations are looking up the potential. Because helium-3 parts per billion are comparatively low, even in the Moon's regolith, it would be logical that whoever would be mining for helium-3 would also be mining for something else in the regolith simultaneously. But what is it made up of? As happens to be the case, the Moon's regolith is filled with various minerals. Observe this false color mosaic of the Moon, with each color showing various deposits of minerals on the lunar surface. There are many metals to be discovered on the Moon in large amounts, such as iron, titanium, aluminium, silicon, calcium, and magnesium. Part of these metals are bonded into difficult-to-reach minerals and oxides. However, isolating the metals will also frequently yield beneficial byproducts, such as oxygen and hydrogen. They are extremely basey and not scarce on Earth at all. But releasing these elements in the Moon itself will make it possible to a colony that will be self-sufficient. Since oxygen equates to breathable air, hydrogen can be used to make fuel, and marrying the two will yield water. Untreated regolith may also be beneficial, as it can possibly be made into lunarcrete, which is of use in the construction of infrastructure for the Moon without having to ship the materials from Earth. Glass would also be easily manufactured from lunar regolith, and although it's not really perfect, it is possible for some plants to grow in lunar regolith, making any lunar base independent in growing its own food, short of hydroponics. But the most significant resource discovered on the Moon are, ironically enough, metals called rare earths. Curiously, rare earths, which make up this part of the periodic table, are not technically that rare on Earth. However, the problem with mining them is that they have not actually accumulated into large deposits. Instead, they are scattered throughout the Earth's crust. This is to say that they are very difficult to mine on our planet, and only a handful of countries around the globe possess large deposits to do anything about that. Even then, most nations don't bother at all due to the immense environmental and human devastations that result from pollution of mining them. The only nation that did not falter from these issues is China, since China possesses approximately 30% of the world's rare earth supply, and since it is among the only nations to mine for them, they command a 95% domination of the market. 95% domination of the market places China in a dominant position in the entire world, particularly considering that these minerals are so vital to our society, being pieces of all sorts of electronics and batteries. Due to the enormous surge lately to transition to electric cars with their gigantic battery packs, demand for these materials will do nothing but grow, so it's worth taking into account where the minerals constructing the batteries originate. Are nations with relatively substantial deposits, such as the US, Canada, Australia, and South Africa, going to begin excavating their backyard in order to draw them out? Or instead of further contaminating the Earth in our efforts to become green, is it really more practical to retrieve these rare earths from the Moon anyway? Rare earths are no more plentiful on the Moon than here on Earth, however. There are some deposits have already been on the cards, and pollution on the Moon will definitely have none of the disastrous environmental and human repercussions associated with doing it here. With increasing demand for these elements bound to rise in the next few decades, it may well be that mining for them on the Moon becomes economically feasible. And not just that, but a monopoly of the market is a monopoly of the market price, and whoever holds control of the market will gain a huge advantage. Will it be China continuing their dominance? Or will some of the other space-traveling nations and corporations want a slice of the pie? Only time will tell. Which brings us to another interesting question. Who actually owns mining rights? On the Moon? Well, it's sort of unclear. The primary space treaty, which most nations in the world have signed up to, is called the Outer Space Treaty, and deals with things like disallowing weapons of mass destruction in space, disallowing military bases in space, and disallowing claiming any celestial body. However, it doesn't really cover mining. Other treaties have been put forward which would cover mining in space, But so far, only non-spacefaring countries have signed up for it. Right now, it could just be a matter of first come, first served. This makes it all the more essential to map the surface of the Moon and discover sources of usable lunar water. If we ever plan on colonizing the Moon, using this water will be of immense importance. But gathering this water ice would be more difficult than you'd imagine. And I don't just refer to the cold. There are larger issues we'd need to deal with if we're going to gather and utilize water ice and other materials from the poles, one of which is electricity. Due to the Moon's low inclination, solar winds, mainly made of ions and electrons, pass by the polar regions and the terminator almost horizontally, hitting the crater's leeward. Once there, the negatively charged electrons, which are 1,000 times lighter than the positively charged ions, rush down into the crater's inside walls and bottom, causing these surfaces to become negatively charged. As the electrons rush down before the ions, a difference in charge is formed, causing an electric field to form. A negative charge is created at the bottom and inside walls of the craters, while a positive charge forms above until the positively charged ions are driven into this electric field by the electrons. As you can imagine, the most prominent separation between the two occurs at the crater's leeward, where the solar wind hits. This division between electrons and ions will eventually build up to a critical point. Due to this phenomenon, these regions might be surged up to hundreds of thousands of volts, which might prove fatal to an unsuspecting adventurer. But even if you skip the poles, that may not be the last of the electrical issues you might face. On the Moon. Another happens when combined with the fine surface dust of the Moon. Regolith. The Moon has no magnetosphere, so any incoming solar winds directly hits its surface, causing the surface to become negatively charged, and the covering fine dust on the Moon, regolith, becomes electrostatic. Regolith is a fine dust with sharp edges which have abrasive properties. Actually, during the Apollo missions, it was experienced that regolith stuck to anything because of its electrostatic charge. This can actually harm spacesuits and equipment, which would be an enormous issue. Moreover, regolith also creates some adverse effects on health-inducing eye redness and cough, since it is able to be extremely poisonous. Spacesuits during the Apollo missions were produced from a material known as woven Teflon, which picked up the electrostatic regolith and trapped it into its material. Woven Teflon can also produce a triboelectric effect, making the astronauts a medium between the negatively charged ground of the Moon and the positively charged solar wind flowing above their head. This is similar to what happens when you rub your feet on a carpet and then touch the metal handle of a door, causing you to get a small electric shock. A laboratory experiment has even proved that woven Teflon with a simulant regolith covering was more likely to be electrically arcing. Lunar exploration wouldn't be nearly so good if you were always getting electrically shocked. So if the regolith and the woven Teflon made the astronauts that sensitive to being electrocuted, why have we not seen it before? Wouldn't it have occurred in the Apollo missions? Well, this static buildup can be mitigated when photons released by the sun initiate some of the electrons in the ground in a process called photoelectric emission. This will make the ground to be more positively charged and counteract the negative charges transported by the solar wind. Because the Apollo missions landers landed on a region of the Moon which was bombarded constantly by sunlight, our astronauts had extremely low chances of being electrocuted. But that's not to say it would not be a problem somewhere else. So, how do we make our astronauts safe from very hot or cold temperatures, poisonous dust that might potentially infect bases on the Moon, and the very high likelihood of astronauts being electrocuted by as much as hundreds of thousands of volts of electricity? To prevent that, we would need to construct a new spacesuit with dissipative qualities that would never let possibly harmful electric discharges to harm them or hurt the astronauts in them. You may think a good insulator is rubber, and you would be correct, but that would have to be weighed against the extreme temperature extremes that these suits could be subjected to. After all, What happens to rubber in an environment where temperatures could easily be minus 247 degrees Celsius? There are several working on projects despite those that are attempting to come up with a solution to these and other issues, but nothing concrete has resulted from it so far. To steer clear of regolith, a team at the Washington State University received $130,000 from NASA on a liquid nitrogen project, which has properties that make it able to trap dust, such as regolith, off surfaces, enabling lunar bases cleaner and prevent contamination risks of getting it. NASA is also developing AO technology called electrodynamic dust shields, which are electrically charged panels which, by means of wires, fire currents capable of erasing the regolith from surfaces. A very neat method of cleaning. There is yet a new revolutionary technology being crafted by Intention, a Norwegian technology firm that is developing a project named ASG. This technology may potentially facilitate remote human explorations and missions through a human-machine interface that enables individuals to drive rovers, robotic arms, or even machines with the movement of one hand. They are developing to integrate this technology into spacesuits that might have interesting ramifications for future missions to the Moon, and indeed Mars. This would enable astronauts to remain safe in bases while the machines are getting it done on the field. It's exciting to see different hurdles being overcome in the mission to find and gather lunar water, but while there are successes, there are also failures. In July 2024, NASA announced that it was canceling its volatiles investigating polar exploration rover, Viper, which had been meant to be the first ever such mission to venture into the Moon's south pole and look for water ice. The mission had been meant for 2023, but because of delays in the construction of the rover and a shrinking NASA budget, Viper was postponed to 2025 and eventually canceled altogether. The rover, already constructed, can be cannibalized for spare parts. That's a heavy blow, since there's no other U.S. project in the next few years planned to possess the same level of capability as Viper, which was mobile and was able to explore not only the surface of the Moon, but its subsurface, to see if water ice could be found there. Many scientists outside of NASA were surprised at the cancellation, with some calling it a dark day for lunar science. Hopefully, another space agency or company will step in to make use of the operational rover. Otherwise, it seems to me to be a complete waste of time, funds, and skill. NASA is not alone in discovering lunar exploration to be difficult. 5 out of the last 9 attempts to land on the Moon failed. But even if they had succeeded, maybe they would have been surprised, as it appears that lunar water, that valuable resource crucial to the formation of any human settlement on the Moon, is surprisingly difficult to actually find. We've kept finding it over and over again in spectroscopy. And yet, when we have a close look at where it should be, instead a mystery is found. The established belief among scientists today is that the permanently shadowed regions of the Moon are one of the most likely places to find frozen water ice. But because it's so dark down in these craters, it's difficult to know for sure exactly which craters house what. It would be unfortunate to establish a scientific foundation, only to find that the crater beside you was utterly void. Unfortunately, LRO, the NASA lunar imager charged with charting the entire surface of the Moon, has its limitations. Its onboard imager, LROC, is not powerful enough to penetrate this darkness. But there is now a new camera orbiting the Moon that is able to. The reason why I mentioned previously that 6 nations had launched probes to the Moon prior to December 2022 is because on 16th December, that figure actually increased to 7. Following a 412-month-long journey, South Korea's Danuri probe just entered lunar orbit. And Danuri's findings gave even more details about lunar water, and generating even more questions. NASA actually collaborated with South Korea fairly closely in producing Danuri, giving them scientific skills and communications and navigation assistance in a spirit of international, cooperative scientific joint working. As a thank you, South Korea's Carry space program donated 7 kilos of space aboard their Korea Pathfinder Lunar Orbiter, KPLO, or Danuri, as it's nicknamed, a composite term constructed out of dal, meaning moon, and nurita, meaning enjoy. NASA pondered what science instrument could best be installed on Danuri, and in the end, they chose a device called ShadowCam, a younger brother of LRO's own narrow-angle camera, with one very significant improvement. With its 200 times sensitivity, it makes pictures such as this appear like this. This very clear picture is of Shackleton Crater, located at the Moon's south pole, the first ever place to be photographed by LRO. And now, thanks to Danuri and ShadowCam, we can correctly peer into its inner basin. It happens that Shackleton doesn't appear to be that dissimilar from most of the other craters on the Moon. Its crater floor is speckled with bumpy hummocks, but curiously, there is no apparent ice here. Maybe it's because Shackleton is a smaller crater, so that temperatures inside do not get quite so low as would be required for ice to form reliably. One thing to note is the evident track left by a boulder rolling down the crater wall, seen near the top of the image. Tracks like this are a common sight on the Moon, since in the absence of wind, any disruption of the dusty surface is never buried again. This trail might be very old. I mentioned that maybe the reason no ice was discovered in Shackleton was that Shackleton was a little crater, but ShadowCam has now looked into numerous various craters in both the North and South Pole areas, and to date its findings have only added to the enigma of lunar water. Despite Chandrayaan-1's revelations all those years back, none of ShadowCam's imaged photographs displayed the characteristic sheen of water ice, either in the form of glaciers or light dusting of frost. And it only becomes more bizarre when we learn of one of the results from India's Chandrayaan-3 mission. It was Chandrayaan-1 that initially found evidence of water on the surface of the Moon. But Chandrayaan-3 would look even more closely, only for its results to return rather different from what scientists had anticipated to observe. India's Chandrayaan-3 moon mission was already historic in nature. It placed India in the books of history for being the fourth country to ever successfully land a space vehicle on the Moon, and the very first to ever land at its south pole, Sorry Viper. The rover Pragyan and lander Vikram already made findings that have the potential to greatly influence our understanding of the chemical composition and geological past of the Moon, and has provided the world with crucial information that will help inform return missions to our lunar neighbor. And yet, despite all the accolades, and deservedly so, it's what Chandrayaan-3 did not find out, but ought to have, which I find to be the most interesting. Have you also noticed it? India's counterpart of NASA ISRO, the Indian Space Research Organization, issued press statements prior to the launch, and there was always something they said they were mainly there to discover. One reason the South Pole was selected out of all other places. One enigma regarding the Moon that is growing more profound the more we research, and yet must be resolved before we can reasonably hope to begin establishing permanent bases there. In short, where is all the water? Chandrayaan-3 was launched on the 14th of July 2023. It was made up of a lander module called Vikram, a small rover called Pragyan, and an orbiter module that carried the other two components across the gulf of space. On the 23rd of August, Vikram, with little Pragyan tucked inside, touched down on the Moon's surface at the start of a lunar day. Time wasn't with them, though. Chandrayaan-3 was shockingly budget-friendly mission. Although NASA's Artemis mission launches will cost on average $4.1 billion, the whole Chandrayaan-3 mission cost only 6.15 billion rupees, or around $75 million. Ironically, less than what many recent blockbuster space movies cost to make. Maybe Hollywood should think about filming their next moon movie on location. But with that reduced budget came technological restrictions. When the lunar night descended, Vikram and Pragyan would be exposed to temperatures of 120 degrees Celsius, temperatures they were not designed to endure. A lunar day lasts 14 Earth days. The Chandrayaan-3 mission would have to do its key goals during that period, since their chances of reaching the day after next were low. And so Vikram extended its ramp, and Pragyan the rover began to power. Up and went out, down onto the surface of the moon. Pragyan is a 27-kilo 6-wheeled rover, which arrived equipped with an alpha particle X-ray spectrometer, APXS, for the analysis of the chemical composition of the moon by firing radiation at it and seeing what wavelengths bounced back, and a laser-induced breakdown spectroscopy, LIBS instrument. That does a similar thing, but this time by firing a laser on the point of interest and examining the wavelengths of light emitted by the resultant plasma. The two instruments combined would suffice for Pragyan to try to locate water or any other interesting compounds, verifying their makeup for scientists once and for all. And thus, it got to work sending both devices on the ground alongside it. Within days, the findings began pouring in. Aluminium, calcium, iron, chromium, and titanium were all discovered on the moon's surface, and other fascinating elements such as oxygen. Indian scientists were most thrilled with the first ever in situ measurement of sulfur at the moon's pole. Sulfur is a thrilling element to discover, since it can tell us about the evolution of the moon over time and shows that there once was volcanic activity in the area. But despite all of these findings, there was one aspect which was not appearing in the analysis. The crucially important hydrogen was conspicuously absent. Pragyan embarked on finding out more in the wider area. Controlling the rover was all done manually by scientists on Earth, monitoring Pragyan's onboard navigation camera. This had to be done very carefully, since the signal delay between Earth and the Moon meant that commands for the rover to stop were delayed by a little less than 3 seconds, time that could make all the difference if the little 6-wheeled rover wasn't going to overturn. And in fact, this nearly occurred. Early on in Pragyan's mission, the rover was required to briskly halt in order not to drop into a big 4 crater scientists hadn't initially realized was there. I mean quickly. Pragyan's move speed was 1 centimeters per second, not quite the quickest of sprinters. In its 2-week existence, Pragyan didn't move more than 100 millimeters from Vikram. Luckily, the crater was found before it was too late, and scientists could reverse and take another path. But if you take a look at Pragyan's path, you see that there was a second instance where Pragyan did not go down into a crater it encountered, rather deciding to go around. No pictures of this second to determine that no ice was seen there. Vikram itself did not waste time during this period. It conducted temperature measurements of the moon's surface, excavating 10 centimeters deep to take the moon's temperature at various depths. It gauged the plasma composition of the atmosphere. Welcome news. There isn't much there, so radio communication to the moon probably won't receive much interference. It picked up a potential moonquake which, with the small 2-week window, was some great timing. Right at the end of its trip, in a fit of last-minute zeal, the Vikram lander even successfully executed a 40-centimeter high hop, firing its boosters to elevate itself from the ground, traveling 30-40 centimeters along from its last destination. Indian scientists had wished to test how straightforward it will be in the future for landers to someday launch themselves into orbit again from the moon. And this was a good warm-up. None of this assisted the Chandrayaan-3 mission in discovering water ice, however. By 4th of September, the clock ran out. Vikram and Pragyan were both ordered to power down. ISRO scientists had hoped to be able to wake them up again once the night ended, but this hope proved to be fruitless. The 2 lunar explorers had communicated with the Earth for the last time. ISRO and the scientific community at large praised their efforts and declared the mission a success. And rightly so, for India had collected first-hand information from the moon that would be very useful in constructing a picture of conditions at its poles, as well as increasing our knowledge about the moon's history. But it certainly leaves room for a mystery. When I first learned that water ice had been found on the moon, I pictured in my head icy ice lakes, or maybe penitentes that were tall. Maybe a light frost, as vapor from the moon's atmosphere ended, up being trapped in these darkened craters, freezing over the surface and accumulating over time. We have been told by orbiters such as Chandrayaan-1 that water ice is present indeed in these craters, and yet Chandrayaan-3 has followed other missions in failing to actually observe this ice for themselves. Since Pragyan's examination of the lunar regolith showed no evidence of water molecules, where then is the water ice that Chandrayaan-1 found? Though this mystery is puzzling, Chandrayaan-3 gives us a probable solution, not by Pragyan's investigations. It's Vikram that perhaps gave the clue. When Vikram employed its CHAS-T temperature sensor, it could record 10 various readings of the temperature of the moon, beginning at the surface and proceeding downwards in 1 centimeter intervals. What it measured in the space above the surface of the moon was a temperature a bit short of 60 degrees Celsius, far too hot for you to be strolling about in if you were on the moon and somehow didn't mind the absence of air. But interestingly, as CHAS-T sampled deeper and deeper below the surface, this stifling temperature fell off rapidly. At 8 centimeters deep, the new temperature Vikram was sensing was 10 degrees. That's quite a plunge. From this we can deduce that lunar regolith is such a bad heat conductor. But that also suggests rather strongly that the very best location we're going to find ice is not lying on the surface of the moon, but actually we need to look below it. There's a lot we don't know about the moon and its hydrological cycles. There's increasing evidence that the moon has a great amount of water, and yet it will be extracted only with understanding where this water is to be found, and how it flows during the long lunar day and night. Does solar radiation have an effect on it? Is it trapped in hidden deposits? Although Chandrayaan-3 only lasted 2 weeks, which I'm sure is less time than ISRO scientists would have liked, it has offered us vital insights into conditions on the moon. As far as water is concerned, at the very least, it has offered future astronauts this one tip. If you want to locate a cup of water on the moon, you may want to begin by bringing a shovel. I'll see you next time.